Hello and welcome to the 4.6 notes. This is a section about the mean value theorem, and we'll use the acronym MVT to denote the mean value theorem. And we're also going to talk about a similar theorem called the Rolle's theorem. Okay, so I want to focus here on the mean value theorem, and it says that we have if a function f is continuous on the closed interval from a to b, and it's differentiable on the open interval ab. And I'm just going to come over here, and I'm going to draw a picture of that. So I'm going to draw a graph, and I'm going to call this the x-axis, call this the y-axis, and I'm going to draw this as a function, and we're going to call this f of x. Okay, so f of x. And I'm going to put a point here on my x-axis and call it point A. I'm going to put another x value here and call this b. So here I have my closed interval from A to B. Okay, and so what you can see is that we are continuous along that closed interval and we are differentiable. Okay, so, but what the theorem then states is that that if those conditions are met, if we are continuous, okay, on the closed interval and we are differentiable, then there is at least one number c in the open interval from a to b such that, and I'm going to come in here and write the actual theorem, but what we want to write is that we have f prime of c, the derivative at some value c, is equal to the average rate of change between a and b. So that's f of b minus f of a all over b minus a, okay? And so let's go ahead and draw a picture of what this is, okay? And so I'm going to come over here back to my picture, and I'm going to draw the average rate of change, okay? And the average rate of change is the slope between 2 points, okay? This slope here is f of b minus f of a all over b minus a, okay? And what the mean value theorem tells me is that there is some point in between a and b, there is some value c in between a and b such that the slope of the tangent line is equivalent to the slope of the secant line, okay? And so I'm going to come in here and I'm going to say that this slope m is equal to f prime of c, okay? So, and this is true for any differentiable function that's continuous over a closed interval, okay? And so one of the things that we can say, all right, you know, this is the formal definition of the mean value theorem, but we should also come in here and say that the slope of the tangent line is equal to slope of the secant line, okay? Okay, another way that we could say this is that this is where the instantaneous rate of change is equal to the average rate of change. Okay? And so that's how we can draw this conclusion. So if these conditions are met, okay, if I have that, if we are continuous on a closed interval and we're differentiable on the open interval, then we are guaranteed to have at least one number c in that closed interval where the slope of the secant line is equal to the slope of the tangent line, okay? So where these two things are equal. All right, so what I want to do now is talk about Rolle's theorem, okay? And what we have here is that if the y values at f of a and f of b are equivalent, okay, if those are equal, then we have a special case of the mean value theorem called the Rolle's theorem. Okay, so if, if f is continuous on the closed interval from a to b, and it is differentiable on the open interval from a to b, and if we know that f of a is equal to f of b. So let's go in here and let's draw a picture that shows this relationship. Okay, so I'm going to draw a y-axis here and an x-axis. Okay, and I'm going to have some function that looks like this. Okay, and I'm going to call this x value a, and I'm going to call, okay, so if there's a, then I have a corresponding y value of f of a. Okay, and if I find another point on here, let me call this b, okay, such that this point over here, right here, is also is equivalent to f of a. So I'm going to call that, which is also f of b. Okay, all right. Then we are guaranteed, okay, all right, so if this condition is met, if we have a function f, okay, that is continuous and differentiable, so continuous on the closed interval, differentiable on the open interval, then we are guaranteed to have some value c in between a and b such that f prime of c is equal to 0. Okay, and by that picture, okay, let's draw a picture of that. So there has to be some value in here c to where we have a slope of 0, so that f prime of c is equal to 0. All right, and so and let's just go ahead and write this, that the slope, okay, of the tangent line, okay, there is a slope of the tangent line that must be 0. Must be 0. Okay, and the other thing we could say is that there is a horizontal tangent between any pair of roots. Between any pair of roots. Okay? So, and this is just a special case, all right? But the main thing that we want to talk about is the mean value theorem, okay, and show that that works for any continuous function and that is differentiable. Okay, this is a very powerful theorem. We're going to use this a lot throughout the year. So let's go ahead and take a look at some of the practice problems here. And so the first example says, show that the conditions for the mean value theorem are met and find the c that the mean value theorem guarantees for this function, okay? So what I want to do is, talk about how we can show the conditions are met, okay? So the question is, are we continuous on the interval from -1 to 1? Okay, so are we continuous? And what we know is that this function here is, this is a polynomial. Okay, so this is a polynomial. So we know that it's always continuous, and differentiable. Okay, so we know that this will be a, that this does satisfy the mean value theorem. So the first thing I want to do is find the average rate of change, okay? So let me find the average rate of change here. And so I'm going to find f of 1 minus f of -1 all over 1 minus -1, okay? So if I were to plug in 1 here, okay, and let me go ahead and do that. I'm going to do that over here on the side. If I found f of 1, then that's going to give me 1 cubed minus 1 squared minus 2 times 1. Okay, so that's going to give me 1 minus 1 minus 2. So 1 minus 1 is just 0, minus 2, which just gives me negative 2, okay? So I'm going to come in here and I'm going to write that this is equal to 2 minus, and what happens when I plug in negative 1? And so I'm going to do f of negative 1 is negative 1 cubed minus negative 1 squared minus 2 times negative 1, okay? So I get negative 1 minus 1 and then plus 2, okay? So this is going to give me negative 1 minus 1, that's negative 2 plus 2, so that's going to end up just giving me 0. So I end up having negative 2 minus 0 over 1 plus 1, which is going to end up giving me negative 2 over 2, which gives me a value of negative 1, okay? So this is the slope between the 2 points, okay? This is the slope of the secant line. Slope of secant line, okay? Now, what I want to do is I want to take my derivative of my function f, okay? So if I take my derivative, I'm going to get f prime of x is equal to 3x squared minus 2x and then minus 2, okay? And what I want to do is I want to set my derivative equal to negative 1. So I'm going to go ahead and do that. I'm going to write negative 1. Now I'm going to plug in c for x because that's what we're trying to find based off of our theorem. So I've got 3c squared minus 2c minus 2, okay? And I'm going to go ahead and add 1 to both sides, And so I get this. I get 0 is equal to 3c squared minus 2c and then minus 1, okay? And that's actually going to factor out to 0 is equal to c minus 1 times 3c plus 1, okay? And so if I solve each of these for c, set c minus 1 equal to 0, I know that c is equal to 1, and then 3c plus 1 equal to 0, then I know that c is equal to negative 1/3. Then I need to look and see which one of these values is in between negative 1 and 1, and this is my value here. Okay, so the value is c is equal to negative 1/3 is what we're looking for. Okay, I'm going to go ahead and stop this video, and I'm going to work on the next few examples, but hopefully this is a good start for you, and we'll see you in a bit. Thanks. Bye.